All right, 8th grade. So this is the Unit 4 function review, getting us ready for that Unit 4 test, which is on Monday, February 5th. So again, this is our function unit. So throughout this unit, we've looked at functions and non-functions. We've looked at linear functions. We've looked at tables, equations, and graphs that represent both linear and non-linear functions. Before we get into this packet, we're just going to take a quick step back and just kind of briefly go over what exactly a function is. So before we get into functions, we need to understand that in math we have what are called relations. And a relation is where you have some inputs into this relation and you get out these outputs. So these can be numbers, they can be letters, they can be codes if we're talking about computer programming or computer science. But basically the idea is that you have this set of things that you put into this relation or this code, and they spit out these outputs. So an example would be, if we had this set of numbers 1, 2, and 3, we put it into this relation y equals x squared. We can call these our x's, and then we would get out the outputs, our y's would be 1, 4, and 9. So you put a 1 in, you get out a 1. Put a 2, you get out a 4. Put in a 3, you get out a 9. So this would be the relation with our inputs and our outputs over here. Now, within the world of relations, we have a specific type, which are called functions. Now, functions, being the name of this unit, are going to be pretty important in math both this year and as you go through high school. So a function is a relation where each input has one and only one output. And what I mean by that is if we have this set of input values, let's say A, B, and C, and then they are mapped onto a set of output values, X, Y, and Z, that A only goes to X, B would only go to Y every single time, C would only go to Z. Now, let's say we added another input value D, and D also mapped onto Z. This is still okay. This is still a function because this input value is still going to only one output value. What would make something a non-function is if we had this input value 1 and sometimes it went to A and sometimes it went to B. So regardless of what these are, they can be letters or numbers, this is not a function because this input value 1 has two different outputs, and we can see that that contradicts this function definition. So this is going to be really the foundation of this entire unit, and then within this, we can get more into the, the linear versus nonlinear, and then looking into equations. So if we get right into the first page of this review, this whole first page is just asking, determine whether or not the following relations are functions, and so we're going to stay grounded in this definition where each input has one and only one output. So we're going to do number 1, 6, 11, and 12 together. In question 1, we're going to determine if this is an input by looking at each of these input values. We have 1, 2, and 3. So I see that 1 is only mapped to 6, 2 only goes to 8, and 3 only goes to 9. So none of these input values ever go to another number. So we can say that yes, this is a function. Now, what we should be looking for, something that wouldn't be a function, is if, for example, we also had the coordinate point 1, 7, because if we also had 1, 7 in this set, then we would have this input value 1 sometimes being mapped onto 6, but also being mapped onto 7. So if 1, 7 was part of the set, it would not be a function, but since it is not, and each of these inputs has one and only one output, we're all set. This is a function. Now, I want you to pause the video here and do numbers 2, 3, and 4. I'm just going to give you the answers, but we're not going to have time to go through all of these. So number 2, yes. Number 3, yes. And number 4, yes. So each of these first 4 are functions. All right, so looking at numbers 5, 6, 7, and 8, we're asked if these are functions or not. Now, I think the best way for you to do these is get out a piece of scratch paper or graph paper, and you can either make a table or a graph. I think that the tables would probably be the most clear, and then putting them on the graph, but we're just going to do some sketches here. So for number 5, I see that this is an equation written in slope-intercept form. So I'm just going to sketch a quick coordinate plane. In this equation, we have the y-intercept of 1. We could say that that was here, and a slope or rate of change of 3. So that means this line, if we were just to draw a rough sketch, would look something like this, with arrows on the end, meaning it is going both ways forever and ever. Now, the reason that this is a function, let's see if we can zoom in a little bit on this. The reason that this is a function is because, again, each input has one and only one output. So if I picked a specific x value, let's say the x value 1, I would find that there's only one corresponding y value. Now, when we're looking at graphs, we do what's called the vertical line test, where we can drag our pencil and see that it never crosses this graph at a specific time more than once. So this one, say yes, this is a function. Now, if we were to look at, let's say we looked at number 7 and did the same thing, we can quick sketch a graph. And we wanted to draw this line x equals 6. Now, we did this in the do now last week, but as a reminder, this is the line where every x value on this line is 6. So you can set our x value as 6 if we were looking at coordinate points and pick anything else. So for example, 6, 1, 6, 3, 6, 0. And if we started to plot these lines, they would form a straight line that looked like this at this x value 6. Now we see that as we do this vertical line test, we fail right here. The reason we fail is because this input value 6 has more than one output value. It actually has infinitely many output values, and because of this, we say that no, this is not a function. Now for number 6, you can do this similarly to number 7, but notice that your line should be horizontal rather than vertical. And then for number 8, I recommend making a table of values and then plotting that on a coordinate plane to determine whether or not this is a function. So right now I want you to pause the video, do number 6 and number 8, and then push play for your answers. So number 6 and number 8 are both functions. Now you might have been a little confused on number 8 because it's not linear, but remember when we're thinking about functions on a graph, we're only thinking about the vertical line test. All right, so just 2 more on this page. Number 11, seeing if this is not a function. So we'll start to look at these input values. I see that 2 is being mapped to 3, 4 to 2, 2 to -5, and 6 to -3. Now, right away I notice that we have this x value 2 twice, And I see that it's being mapped onto different y values. So because we have this input going to two different outputs, we can say that no, this is not a function. All right, the last one we're going to do here is number 12. And for this, we're going to use the vertical line test that we got a little into in numbers 5 through 8. So if you slide your pencil across this graph, you notice at any given point, I'm only crossing the graph at one point. So for example, if you were to draw a vertical line, I'm only crossing the graph here. If I were to draw a vertical line here, I'm only crossing the curve or the graph right there. So at any of these points, we're only ever crossing that curve one time. So we say that this passes the vertical line test, and yes, this is a function. All right, so now I want you to pause the videos, do numbers 9, 10, and 13, then push play to check your answers. All right, so for both number 9 and number 10, we're saying yes, these are functions. And then for number 13, we can say no, this is not a function because it fails the vertical line test. All right, so we've done functions, and now we're going to get into linear versus nonlinear. So we're just going to do two examples on this page. We're going to do number 2 together. So in number 2, we're looking at this equation y equals x squared minus 2. If you think back to when we covered this the first time, just looking at the form of this equation, we're able to say that this is nonlinear, or it is not a straight line. Because in order for something to be linear, it needs to have a constant rate of change. And in an equation, that means that exponent on our x needs to be 1. I see right here, this exponent is 2. So right away, this is telling us we should probably try and prove that this is nonlinear. So to prove that this is nonlinear, we're just going to pick a couple x values and calculate a rate of change. So we can pick x value -1, 0, 1, and 2. Now if we substituted these into the equation for x, -1 squared minus 2, 0 squared minus 2, 1 squared minus 2, and 2 squared minus 2. If we were to evaluate each of these, -1 squared is 1, minus 2 gives us -1. 0 squared is 0, minus 2 gives us -2. 1 squared is 1, minus 2 gives us -1. 2 squared would be 4, minus 2 gives us a +2. So we substituted our x values to get the corresponding y's. Now we're going to calculate our rate of change. So if we looked at between these first two coordinate points, -1, -1, and 0, -2, the change here, -2 minus -1, would be a rate of change of -1, excuse me, a change in y of -1, and then 0 minus -1 would be +1, our change in x. So the change in y being -1, change in x is +1, gives us a rate of change of -1 between these first 2 points. Now, if this were linear, we would need to find a rate of change of -1 between each of these points. Now, if we look at these last 2 points on our table, 2 minus -1 gives us 3. This is our change in y. But then when we calculate our change in x, 2 minus 1 is 1. So the rate of change between these 2 points would be 3 over 1, or 3. So between these 2 rows, we have a rate of change of 3. Between the first 2, we have a rate of change of -1. So therefore, we can confirm our hypothesis that this, in fact, is nonlinear. So now I want you to pause the video and do number 1, Similarly here, pick any x values you want, find the corresponding y's, and prove that it is linear or nonlinear. So for question 1, if you were to plug in any x values and get out corresponding y values, we would say yes, this is linear, and you'll notice that this exponent on the x value or x variable is 1, which gives us that hint that this will be linear. All right, the last one on this page we're going to do is number 18. Determine if this graph is linear or nonlinear, and then if it is linear, is it increasing or decreasing? So just looking at this graph, I see that this is a straight line. If we pulled out some points here, we see that it does also have a constant rate of change. The rate of change here is 2, so between each of these we run up 2 over 1, up 2 over 1, up 2 over 1, and so on. So that we can say that it is linear because it is a straight line, has a constant rate of change, and then we have to now determine is this increasing or decreasing. Now just looking at this, we read left to right in a sentence. We're also going to read our graph here left to right. So as we move right on this graph, we want to think, are we increasing or decreasing in our y values? And you'll see that my pencil is going up, so we are increasing. These y values are getting bigger, so we can say it is linear and it is increasing. So now you can pause the video, do number 16 and 17. Great, so for both of these, we can say that they are both nonlinear. Right away, we can see that they're not straight lines. The way that you would prove this is pick at least 3 coordinate points on both of these curves, show that you can find different rates of change, therefore you can prove that they are nonlinear. All right, so we've been talking about rate of change as we were talking about linear. Now on this third page here, we're going to be comparing rates of change. So in each of these numbers 1, 2, and 3, we want to know which function A or B has a greater rate of change. Now function B is a little easy because it's in slope-intercept form. This tells us that our y-intercept is -1, and our m value is 5, and this is our rate of change. So in function B, we have a rate of change of 5. Now we're going to compare that to function A. So in order to calculate the rate of change on a graph or on a coordinate plane, you just need to find at least 2 coordinates. So we can pull out the coordinate point 1, 1 and 3, 3. If we were to calculate this rate of change, 3 minus 1 is 2. 3 minus 1 is 2, so 2 over 2 gives us a rate of change of 1. So in function A, our rate of change is 1. Now we can compare these. Obviously 5 is greater than 1, so we can say that function B has a greater rate of change. Now one thing to be careful with here is that when we're calculating rates of change, we always need to be calculating the absolute value, because just because a rate of change is negative doesn't mean that it's not changing faster. So again, always make sure you are calculating or taking that absolute value when you're calculating your rate of change. So now I want you to pause, do numbers 2 and 3. Make sure you're calculating rates of changes for both tables and graphs if necessary. Great, so for number 2, function A is the greater rate of change. And then for function B, let's do this one real quick because we have some negatives here. So if we did -5 minus -17, this would be -5 plus 17, which would give us +12, our change in y. And then -1 minus -7, or -1 plus 7, gives us 6 as the change in x. 12 over 6 is 2, so the rate of change here is 2. The rate of change in function A is 3, therefore function A has the greater rate of change. All right, so this is something that we've been struggling with, I think, as a grade, just because it's a little bit harder of a skill. Really tests our knowledge of equality, applying inverse operations, and making sure that whatever we're doing to one side, we are also doing to the other. So I want to convert these equations to slope-intercept form, or y equals mx plus b. You'll notice that in this equation, y is our variable that's isolated, so we're going to want to make sure that y is by itself. In number 1, I see our y value is right here. I always like to draw this little arrow just so that I know what I want to get by itself. So the first thing I'm going to do to both sides is subtract 3x. This will get rid of this term. So on the left, we'll be just left with negative 2y. Now on the right side, I have a negative 16 minus a 3x. Notice that this has a variable and this does not. They are not like terms, so we can't combine them. So we'll just take both of these down, write it as negative 3x minus 16. I like to write the term with the variable first, just because I'm more comfortable with that, but it doesn't really matter. So next, I see we have a negative 2y here. Make sure that you're careful of this sign. Don't forget this negative as we bring this down. So in order to get y by itself, I need to divide both sides by negative 2. So on the left side, we have a y. Negative 3x divided by negative 2 simplifies to 3 over 2x. And then negative 16 divided by negative 2 simplifies to positive 8. So this equation simplifies to y equals 3 over 2x plus 8. Now, I want you to pause the video, do numbers 2 through 6. I'm not going to take the time to go through the answers. There's a lot of equation, editors online. Pretty easy ways to find the answers for these 6. So you guys are on your own. Follow these steps. All right, so we're getting towards the end here. We're getting into the word problems. We're just going to do one of these. So a certain number of apples are placed in a basket and weighed. The table below shows the weights for a certain number of apples. What is the initial value, and what does it represent in the context of this problem? So when we think about an initial value, that's our start. And when we have equations, y equals mx plus b, this is our b value, or our y-intercept. So in order to kind of work backwards to the starting value, we have to see how much each apple weighs. So going between the first and second row here, I see our weight is going from 64 to 68 pounds, a change in y of 4, and the number of apples is increasing from 22 to 24, or a change of x of 2. So 4 over 2 is 2. We can label this as 2 pounds per apple. Now, when we write our equations, y equals mx plus b, again, we're looking for this b value. Now, we just found the rate of change here, so our m value is 2. Now, I also see that we have y, x, and b in this equation. Now, b is what we're looking for, so we're not going to be able to substitute for that. But we need to substitute something in for x and y in order to be able to solve. So if we look back over to our table here, we see that we have these corresponding values, our input and output. This number of apples is going to be your x, your input value, and then the weight, that'll be your y, your output. So we can use y as 64, x is 22. Now we're able to substitute into this equation. So we can rewrite this as 64 equals 2 times 22 plus b. Now we can solve for b, so we can write the next line, 64 equals 44 plus b, and then if we subtract 44 from both sides, we get b equals 20. Now, we found the initial value, but this question is saying, what does this represent in the context of our problem? So if we think, this initial value, or the start, is when we have no apples. So what would cause us to have a weight of 20 apples of 20 pounds if we don't have any apples? And the answer kind of lies here in this first part of this word problem, where we have apples and the basket that are weighed. So this y-intercept means the basket weighs 20 pounds. Great, so if you follow these steps, I'm sure you can do number 2. You can pause the video and we're gonna move right on to the next section. All right, so now we're drawing functions. The reason we're gonna spend some time here on this is because a lot of people were absent this day, and I want to make sure that we have a good understanding of what these real world functions look like on our graph. So we have this paragraph here, and we wanted to put it on this this coordinate plane. The biggest piece that you can do here, the most effective strategy, is making bullet points. So we're going to read this one time and then make our bullet points. So Miss Arth buys $40 worth of stock. Over the first 4 days, the value of the stock increases at a constant rate of $5 per day. For the next 3 days, the value of the stock does not change. And then between days 7 and 10, the stock falls at a constant rate and it finishes at $30. So up at the top here, we have some room to make some bullets. The first thing I see is that she buys $40 worth of stock, or we're going to start at $40. And then over the first 4 days, the value of the stock increases at a constant rate of $5 per day. So on days 0 through 4, it grows at rate of $5 per day. So if we're growing $5 per day over the course of 4 days, we can do 5 times 4, it's going to give us 20. So after 4 days, we should be at $20. So we can just make that coordinate point 420. Now, for the next 3 days, the value of the stock does not change. So that would be days 4, 5, 6, 7. So for 4 through 7, we're going to stay at oh, you know what? We made a little mistake here. So this told us that the stock was going to grow $20, but because we already started at 40, this would actually mean that this would be 40 plus 20. So our coordinate point would be 460. So since we got that sorted out, if we're at $60 and over the next 3 days we stay there, that means that days 4 through 7 we're going to stay at $60. All right, and then next we can see that between days 7 through 10, we're going to fall at a constant rate. We're going to falls. And then we're going to finish at 30. So that means that on day 10, we should be back at $30. All right, so now we can start putting this on our graph. So if we are starting at 40, that means that we can put this coordinate point right there. And then we're growing, so over the course of the first 4 days, $5 per day, we end up at the coordinate point 460, which is right here. We have this constant rate. And then over the next 3 days, we stay at $60, taking us to this coordinate point, 760. So we have 460 and 040. And then for days 7 through 10, we fall at a constant rate ending at 1030. So not a ton here, really manageable. The biggest piece is making sure that we're taking these bullet points before putting it on the graph. So I want you guys to answer questions parts A and B. Use your knowledge of rate of change and you'll be fine. All right, so the last part here is interpreting graphs. So we just drew a graph. Now we got to think about, if we're looking at one, what does it mean? So this is going to give you a little bit of freedom. It's asking you to write a story to represent Mr. Burrow's commute to work. So I see on the y-axis here we have distance from home. So y is distance from home. And then x, this is our time. Now notice that neither of these axes have specific units. So we don't see that we are measuring this distance in miles, meters, feet. And then additionally, we don't see what we're measuring this time axis as, whether it's minutes, hours, maybe days. The biggest point here is that we just want an idea for, do we know what this graph means? So we have three sections here, A, B, and C. And we're thinking, number one, what is happening here? And then how do each of these three sections compare? So as we look at section A, we see that as time increases, so does the distance from home. So maybe this is the part where Mr. Burrows walks to Nashville Prep at 5 miles per hour for maybe 5 minutes. Now, you'll notice that at this point, if we're walking at 5 miles an hour, 5 minutes, and then something happens here, and it looks like we go back to 0. So right here, we're back at distance from home 0, or we're back at home. So, maybe that means I forgot my coffee, my lunch, or, the fantastic test that you guys are taking on Monday. But the bigger piece here is that he goes back home. But you'll also notice that I make it home in a lot shorter time than I was traveling to school. So the big piece here, maybe, I'm running late now. I need to pick up the pace a little bit. He goes back home at, I would say somewhere around 8 miles per hour. So this is going to be an important piece to include, making sure that these rates make sense. This is a lot steeper of a section of this graph than here, and our rates of change need to reflect that. Now, this last section, section C, is even steeper than A or B, and you'll notice that this distance from home is increasing, meaning I'm getting farther away from home. So maybe during this section I make it all the way back to Nashville Prep, but running late, I got to pick up my speed, the rate of change needs to increase. So maybe he drives to NP, and this time maybe I'm driving at 30 miles per hour so this would be a shorter amount of time, maybe 2 or 3 minutes. So notice how important the axes here are. The biggest mistakes that we're seeing is mistaking distance and speed graphs. You'll notice in the second one, the y-axis here is measuring speed, where here we're measuring distance. So just make sure that you're comparing the rates of change and making sure you're making sense of what these axes are asking. So at this point, you really have all the tools, not only to finish this review packet, but really to go into this test confidently. Just make sure that all answers are complete, all questions are annotated, especially when you're being asked to draw a graph. But be confident, y'all got this.